operated by Stanford University for the U.S. Department of Energy, SLAC has been home to the world's longest particle accelerator for nearly 50 years. In 2009, SLAC ushered in a new era in its long history of physics research with a new kind of laser called the Linac Coherent Light Source, or LCLS. The LCLS is the first laser in the world to produce hard X-rays, which can be used to see down to the level of atoms and molecules. Adding almost half a mile onto the original 2-mile-long accelerator facility, the LCLS uses the final 1/3 of the accelerator to produce powerful pulses of X-ray laser light. Scientists at SLAC and from around the world use these powerful beams to explore how atoms and molecules move and behave on some of the shortest timescales imaginable. The LCLS starts with the drive laser, which generates a precise pulse of ultraviolet light, seen here in red. The drive laser pulse travels down to the injector gun, where it strikes the surface of a copper plate inside the gun. The copper cathode plate responds with a burst of electrons, seen here in blue, which are guided into the linear accelerator. Inside the accelerator, the electron bunch encounters the first of 2 magnetic chicanes, or bunch compressors. These chicanes help even out the arrangement of electrons of different energies in each pulse by sending the pulses along a slight S-curve. The compressed pulse emerges from the chicane and is accelerated further, gaining energy as it travels. The electron bunch then encounters the second bunch compressor. The second bunch compressor is longer than the first because the electrons in the pulse now have even greater energy. The electron pulse continues to the end of the accelerator at nearly the speed of light, finishing the boost phase of its ride at an energy over 12 billion electron volts. The electrons enter the beam transport hall, along which they travel through a series of diagnostic monitors and focusing magnets that help keep the beam precisely shaped and on course. Here, into the undulator hall, the electron pulse enters the heart of the LCLS, where the X-ray laser light is generated. The undulator hall houses a long array of special magnets which comprise thousands of alternating north-south magnetic poles, spaced only a few millimeters apart. These alternating poles cause the electron bunch to swerve back and forth in an undulating motion that forces the electrons to give off X-rays. As the electron bunch and X-rays proceed together, they start to interact with each other. The electrons arrange themselves in parallel sheets, causing the X-rays to become in tune with each other, or coherent, with an enormous boost in X-ray power. Once the X-ray laser light is generated, the electrons must be safely discarded before the X-rays can be used for experiments. The beam dump uses a powerful electromagnet to divert the electrons down to a special chamber that absorbs the electrons and dissipates their energy. The X-ray pulse, unaffected by the pull of the magnets, continues on in a straight line. This process happens up to 120 times per second. The X-ray laser pulse is now ready for scientists to use in one of the 6 LCLS experimental stations. The experimental instruments each comprise a suite of vacuum chambers, detectors, and sample environments. Each instrument performs different kinds of experiments, investigating the kinds, arrangements, and motions of the building blocks of matter. For example, the LCLS pulse can be used to make images of single molecules, even though the beam is powerful enough to instantly disintegrate such a tiny sample. Each pulse is so fast that an image is captured in the sliver of time before the molecules can fly apart. Images captured in this way can be strung together frame by frame to create molecular movies of individual biological molecules in action.